So hello everybody. As said, I am Kerstens. I'm here on behalf of the University of Antwerp, and I work at the COSIS lab, which is the Constrained Systems lab of the University of Antwerp. And the COSIS lab is part of the Flanders Makes Strategic Research Center, which develops innovative solutions for the Flemish industry. This paper has been done with the help of Laurijssen and my supervisor, Professor Steckel, who also happens to be the chairman over there. Let's start off with the three questions. What did we do, why did we do it, and how did we do it? So what do we do at the COSIS lab? We have history in making 3D sonar sensors. The system shown here is also the one that was showcased yesterday at the live demonstrations. As shown here, there's a system with one emitter and an array with 32 microphones. And using that array, we can, using beamforming algorithms, steer it into every horizontal and every vertical direction. And that way we can get a full 3D acoustic image of the frontal hemisphere. Applications for these are mostly acoustic imaging is needed, such as complex corridor following and, for example, in wheelchairs, or larger vehicles in agriculture and mining also have applications for this. The energy scape shown here is an example of such an image in which we can clearly see the 4 objects in the room in 3D. What do we want to improve about this? Our previous system had 3 big sides. One system had the acoustic microphones. The other, at the back of that, had a whole bunch of ICs for signal processing and signal conditioning, and then an add-on board that took care of all the ADCs that featured an FPGA. We needed a newer system that was easier to implement, easier to produce, that featured less components. And recently there have been a lot of advances in the MEMS industry that allowed for a more compact system. So what we did here is using low-cost 1-bit MEMS microphones to create a new system. The big advantage of these microphones is that well, they're digital, so they communicate via a very simple 1-bit protocol, just PDM, and you can connect it to a GPIO pin and read it out very fast, which is very handy if you work with FPGAs. So, we have less components that makes for a more compact system, and the space we freed with having less components now has given us the possibility to use an off-the-shelf system like the DE0 Nano system on chip, which I will mention in the next slide. That features all the possibilities to have onboard data processing, and that allows for a standalone system that doesn't need an extra computer, so we can just plug and play this system, just put it on a vehicle and have it interface with the vehicle directly, which is also very handy. Now, how did we plan on doing this? Let's talk about the architecture. Like I said, apart from the big microphone array, the main player here is the DE0 Nano SOC made by Rocket Boards. And a very important feature on this one is the Cyclone V, the Terra Cyclone V SOC. What's so good about this chip for this application? Here is a small overview of the internals. Two very big components here is that it features an FPGA and a dual-core ARM A9 processor. Because we have the dual-core processor, we can run an embedded operating system like Linux. In this case, we use Poky Linux, which is a part of the Yocto project. And because we have Linux, we can easily communicate with Ethernet or easily communicate via GPIO. And also a very handy feature is that there are very fast bridges between FPGA and the HPS side. There are also smaller bridges to configure the FPGA. And also, very interesting is that as the HPS as well as the FPGA are connected to the DDR RAM. There's 1 GB of DDR RAM on this board. And if both the FPGA and the processor can access those, that can allow for a very efficient data handling. Now, how did we structure our system with this? Of course, as I said, the Altera hard processing system with Linux OS, Vue in this case being Pokey, is connected via those hardware bridges using the Avalon protocol. And then we have hardware control interface and an on-chip dual port RAM that's different from the DDR RAM. This is a block RAM on the FPGA itself, which takes its settings from software running on the processor side. And that runs like the pulse we emit to the emitter. Then the hardware control interface communicates with the DAC, which is the pulse that's being sent. And on the other side, we have all the digital PDM microphones, which is the array. Because we use a big FPGA, it's very handy that we can, right after we extract the data from the microphones, immediately do complex computations like ADR filtering, which on an FPGA does not take a lot of time. Then we also have space for more user-specific applications, because not every end user has the same goal in mind. So we also have space to do some custom tweaks. Then the data is ported into a FIFO and then handled back to the DDR RAM. And from the DDR RAM, the Altera processing system, the HPS, can also access the data. And in this case, we now use the HPS to fire all the data through the Ethernet port so that we can handle it with the computer. But the handling can also be done on the Altera itself, and that eventually the only thing that's being given out is there's location, and there is something, there is something, there is something. The small example used in this paper, we demonstrated the use with a small linear array using 6 of these MEMS microphones. We extracted the data, and then we searched for our pulse that we emitted with a matched filter. Then with the beamformer, we steer the array in different directions to look for our sound source. And then with an envelope detector, we can determine the distance at which the sound source is located. Now, what results did we get out of this? Like I said before, in this paper, we used the D0 nano system on chip, along with a prototype 6-element array, which is being connected in entirely the same way as we would connect the 32-bit array. And the results we got out of that was this. Let me guide you through them. This is the raw GPIO data that we pull in. It's a PDM-coded signal. And if we analyze the frequency content, we see our 80 to 20 kilohertz sweep and a lot of noise. This noise, it starts around 100 kilohertz. That's also coming from the microphones, because the microphones feature noise shaping circuitry that make sure that the region of interest, in our case, it's everything below 100 kilohertz, that region is doesn't have a lot of noise, and that all the noise is cast to a non-region of interest. Then using the IRR filter, we can get rid of all that noise, and that leaves us with a very clean representation of the signal we're looking for. So as we can see here, we get a clear representation of our 20 to 80 kilohertz sweep. And then using data from all the calculations, using the data from all the calculations, we can do some good beamforming. And as we can see, here is we located the sound source at minus 30 degrees, minus 10 degrees, plus 10 degrees, and 30 degrees. So we can safely say that these microphones are very well suited in this architecture for applications such as these beamformings. And then the conclusion, because we now have a digital interface instead of the older analog interface of the older microphones, it's very much easier to implement than its predecessor, because now there's less need for a lot of complex circuitry, a lot of components, and therefore it's also a lot cheaper to construct and more powerful, because you can use the space you gained to add other more interesting circuitry. And so we can say that it was about the SPH041 microphones, by the way. You can say that they're very well suited for combining with FPGAs or FPGA-SOCs. And then I will now take questions if there are any.